Hello everyone, my name is Natalia Kharchenko. Today I'm glad to present a revisited version of the hybrid dual lattice attack against the small secret learning with errors problem. This is a joint work with my co-authors Espitau and Antoine Joux. So let's start. Let's start by recalling what is learning with errors. The learning with errors problem was introduced by Regev in 2005. He showed that the LWE problem is probably as hard as certain lattice problems, which implies presumable resistance against quantum attacks. He also introduced the first public key encryption scheme based on learning with errors. Since that time, many variations of the problem were introduced, like, for example, ring versions, and many other cryptographic constructions based on learning with errors have appeared. Now, together with short integer solution, learning with errors is one of the central problems in lattice-based cryptography. One of important applications of learning with errors is fully homomorphic encryption schemes. The fastest existing fully homomorphic encryption schemes are based on the hardness of learning with errors and its ring versions. Now let's move to the definition of the problem itself. To define the learning with errors, it is useful to define the LWE distribution first. We consider the scale invariant version of the problem, so all the things that are usually defined as integers modulo q are defined here as real numbers modulo 1, that is over the torus. We denote the real numbers modulo 1 as t throughout the presentation. Let S be a fixed integer vector and let C be some Gaussian-like distribution over the real numbers centered at 0. Then a sample from the LWE distribution corresponding to the secret S and the error distribution C can be obtained in the following way. First, we sample a vector A uniformly at random. As we consider scale invariant version, each coordinate of A is sampled independently from the uniform distribution over T. Then we sample the error E from our Gaussian-like Xi distribution. Then we return the pair A-B. Here B is the sum of the scalar product of A and the secret S plus the small error E. Now we can define the LWE problem. There are two versions. The decision version asks to distinguish the LWE distribution from the uniform distribution. The search version asks to recover the secret S given arbitrarily many samples from the LWE distribution. In this work, we consider a variation of LWE called small secret LWE. In the original definition of the LWE problem, the secret S was chosen uniformly at random from the set of all n-dimensional vectors over integers modulo some huge number q. In the small secret version, the secret S is sampled from the distribution with smaller entropy. For example, the secret can be a random binary or ternary vector. Many existing fully homomorphic encryption schemes based on LWE or ring LWE use small secrets. There are theoretical results proving that small secret LWE still remains a hard problem. Practically, for some parameters, small secrets can lead to more efficient attack against such schemes. Now, after recalling some basic definitions, let's move to the attacks on LWE. There exist many different attacks. The lattice attacks can be informally divided into three categories: dual attacks, primal attacks, and reducing to unique SVP. In this work, we are developing a version of the dual lattice attack, so we start by recalling how the dual attack works. The dual lattice attack is a distinguishing attack. We are given many samples from the LWE distribution or from the uniform distribution, and the goal is to guess correctly the input distribution. Here, the samples are grouped into the matrix form. Assume that we somehow have an access to a short vector v that gives us a short linear combination of the A part of the input samples. Now, consider two cases. Assume that the input samples came from the uniform distribution. Then there is nothing special about the scalar product of v times b, and it is going to behave as uniformly distributed modulo 1. Consider the case when the input samples came from the LWE distribution. Consider the scalar product v times b. As the samples are from the LWE distribution, it is equal to the following sum. Recall that v is chosen to be such that the linear combination v times a is a short vector. V itself is also short. E is short by the definition of LWE. Then the scalar product v times t modulo 1 should also be short. Thus, to guess the distribution of the input samples, we need to distinguish the uniform distribution over t from some concentrated around zero distribution. To sum up, the dual distinguishing attack can be divided in two steps. First, we recover an appropriate vector v. Second, we distinguish the uniform distribution from some concentrated around zero distribution. The first step, recovering an appropriate vector v, can be performed by lattice reduction. The vector v that we are searching for is a short vector in the following lattice. By finding a short vector in that lattice, we minimize both v and a times v in the same time. A basis of this lattice is given by the matrix B. Here, In and Im are identity matrices, and the lower left part is just filled in with zeros. We can find a short lattice vector by applying a lattice reduction algorithm to the basis B. To obtain short lattice vectors, blockwise lattice reduction algorithms like BKZ are usually used. BKZ works by iteratively finding the shortest vector for projected sublattices of the input lattice. The actual complexity and quality of the output of BKZ is an active research area. And in order to model its behavior, for example, to estimate complexity of lattice attack, we use the following standard assumptions. Let d be the dimension of the input lattice, and let beta be the block size of BKZ. Then we assume first that the BKZ algorithm will terminate after polynomial number of calls to the SVP oracle. Second, that the norm of the vector returned by BKZ is determined by the choice of the block size beta according to the following formulas. Third, that the coordinates of the returned vector are balanced, that is, that they behave like sampled independently from the Gaussian distribution centered at 0. As we assume that the lattice reduction returns a vector with balanced coordinates, we may apply the following trick. Sometimes it can be referred as lazy modulus switching. To distinguish the LWE distribution from the uniform, recall that we need to minimize the following sum. And when S and E come from different distributions, for example, when S is much longer than E, it might be useful to rescale the lattice to make x part smaller. It can be done by adding an additional parameter q and multiplying the top part of the lattice basis by the q and the lower part of the basis by q to the power minus n divided by m to preserve the volume of the lattice. This allows to vary q and balance the two parts of the sum. So that's basically all for the lattice reduction part. Now let's move to the second part of the attack. The second part consists in distinguishing the uniform distribution, modulo 1, from some concentrated around zero distribution. The concentrated around zero distribution corresponds to the LWE input samples. It can be shown that in case of LWE input samples, under the assumptions that we make about lattice reduction, this concentrated around zero distribution is actually a modular Gaussian distribution centered at zero. So the actual goal of the second part of the attack is to distinguish the uniform distribution from the modular Gaussian. The main difficulty in distinguishing the distributions is the modulus in the modular Gaussian. In order to get rid of it, we use the Levy transform. So, in order to distinguish the distributions, we consider an estimator y, which is equal to the average of the Levy transforms of the sample. In case of the uniform distribution, as everything is symmetric, y converges to zero. In case of modular Gaussian, it can be shown that y converges to an exponent of a negative sigma squared times 2p squared. Then, to construct the distinguisher, we just need to take a large enough sample, compute y, and see whether it is closer to zero or to an exponent of minus 2p squared sigma squared. The sample of size e to the power 4p squared sigma squared is sufficient to distinguish the distributions with high probability. The smaller parameter sigma is, the easier it is to distinguish the distributions. Now we are ready to summarize the complexity of the dual distinguishing attack. Basically, the attack needs to call the lattice reduction n times to produce a sufficient amount of samples for distinguishing the uniform distribution from the modular Gaussian. We have a trade-off here. The more time we spend in one run of the lattice reduction, the shorter vectors we get. Shorter vectors returned by lattice reduction implies the smaller parameter of the resulting modular Gaussian. Thus, less runs of the lattice reduction are required. Now, after recalling the dual distinguishing attack, we are ready to move to our hybrid dual attack. The hybrid attack combines the lattice reduction of a projected sublattice with the search for some part of the secret key. That can be done in the following way. First, let's divide the secret S into two parts S1 and S2 of dimensions n1 and n2 correspondingly. We also divide the matrix A of LWE samples into parts such that A1 corresponds to S1 and A2 corresponds to S2. Then we can rewrite our usual LWE equation as follows. In the hybrid attack, we are going to apply the lattice reduction only to A1 part of the LWE samples matrix. We do it in the same way as we did it before in the dual attack. As before, the lattice reduction returns a vector v such that the product of v with A1 S1 plus e is minimized. Then we multiply our equation by v and obtain a fresh LWE sample corresponding to S2. Now v times A2 becomes new A, v times b becomes new b, and the part that we minimize by the lattice reduction becomes a new error e. Thus, we obtain an LWE sample of smaller dimension but with a bigger error, with a bigger noise. As dimension of the fresh sample is smaller, we can try to recover S2 by exhaustive search. Let's see how the search part of the attack works. Assume that we have a small dimensional LWE sample as input. Let's try to guess S2. Let x be a random guess for S2. Then let's compute the difference b minus the scalar product of a and x. If our guess is correct, we obtain a small error e. Otherwise, if our guess is wrong, we'll just get something uniformly distributed. So again, the problem boils down to distinguishing the modular Gaussian distribution from the uniform. The guessing step works as follows. We compute the error e for all the candidates for S2 and return the candidate that produces the most concentrated around zero distribution. To do so, we need many LWE samples from the previous lattice reduction step. We combine them into the matrix A. Then we can also combine all the candidates into the matrix S2. For example, if the secret is binary, the matrix S2 is going to be a matrix of all binary vectors of dimension n2. Then the complexity of computing the arrow E for all candidates is essentially the complexity of computing the product of matrices A and S2. In the small secret case, we can perform this computation faster using the recursive structure of the source space. For example, assume that our secret is binary, that this B is a set of 0 and 1. The matrix of all binary vectors can be constructed recursively. We start with dimension 1, then S1 is just 0 and 1. To go to the next dimension, we just need to repeat the matrix from the previous dimension 2 times and add one additional row, which is zeros on top of the first S1 and ones on top of the second S1. In the general case, this recursive strategy works for any finite set B. To go to the next dimension, we just repeat the previous matrix, the size of the set B times, and add an additional row on top of it in the same way. And this recursive structure is useful for matrix multiplication. Assume that we need to multiply a vector A and our matrix SD. Assume that we already have the result of multiplication from the previous iteration for the vector A without its first element and for the matrix SD-1. Then, to get A times SD, we need to repeat the result from the previous iteration k times and add to it the first row multiplied by A1. The complexity of the recursive multiplication is essentially a big O of the size of the set of the source space. Now we are ready to summarize the complexity of the hybrid attack. The hybrid attack first runs the lattice reduction R times to obtain R fresh LWE samples of smaller dimension. Then, for each candidate for S2, the attack computes the arrow E and chooses the candidate that produces the most narrow round zero distribution. Now the attack has two parameters that define its complexity: the lattice reduction parameter delta and the dimension of the guess n2. And note that in these settings, one run of the lattice reduction gives us one fresh LWE sample. Now let's look closer at the lattice reduction BKZ algorithm. The BKZ algorithm with block size beta works by calling an SVP oracle in dimension beta. Usually, enumeration or sieving algorithm is used as an SVP oracle. The sieving algorithm works by creating and iteratively updating a list of lattice vectors of exponential size in the dimension beta. So we may expect to get many short vectors instead of one in the end. The actual distribution of the output of sieving is not well studied, but we may assume that the number of short vectors returned by sieving is close to the size of the sieving list. Using the whole output of the sieving algorithm, we can decrease the number of times we need to run the lattice reduction. Then the complexity of the hybrid attack can be re-estimated using the following formula. Here we just divide the number of runs of lattice reduction by the presumable size of the sieving output. After estimating the complexity of the hybrid attack, we can use it to estimate the security of fully homomorphic encryption schemes, for example. So we did it, and for several schemes, we found out that our attack leads to re-estimation of the security level for some of them. For example, on this slide we can see the security level of several updates of parameters of TFHE, which is now one of the fastest fully homomorphic encryption schemes. We see that for all the three sets of parameters, our attack gives 0 bits improvement compared to the unique SVP attack that is currently used to estimate security of TFHE. So it would be interesting to compare our hybrid attack and unique SVP attack on a wider range of parameters. This picture presents a comparison for the LWE parameters of dimensions from 200 to 1500 and of noise parameter ranging from 2 to the minus 10 to 2 to the minus 50. The color map shows the difference between the bit complexity of both attacks. We see that most of the time the attacks give similar results, but there are regions where one is better than another. So, for example, when noise and dimension are both big, our hybrid attack is slightly better, and for small noise, USVP attack is more preferable. As the complexity estimation of our attack is based on several heuristic assumptions, we have made some experiments to justify usage of these assumptions. First, we provide a proof of concept implementation of our attack that successfully works in small dimensions. Second, we studied separately the output of the sieving algorithm in small dimensions from dimension 30 to 60 on random lattices of different volumes. For example, this picture presents the distribution of lengths of the vectors returned by sieving algorithm for a random lattice of dimension 50 and volume round 2 to the power 1000. We report more experimental results like this in the paper, and essentially our experiment shows that the sieving algorithm indeed produces many vectors of lengths very close to the expected. To sum up, let's restate the key points of our hybrid dual attack and stress out what's new compared to already existing dual attacks. First, in this work we have revisited and refined the analysis of the dual distinguishing attack with lazy modulo switching, which in particular includes describing an explicit algorithm for distinguishing the uniform and modular Gaussian distribution. Second, we describe the new hybrid attack with efficient recursive algorithm for performing the search part. Third, we propose to use the whole output of the BKZ sieving oracle and provide some experimental evidence to support this choice. So that's all for this talk, and thank you very much for your attention.